Okay, great. Thanks everybody for coming, early. I know for many of you from different time zones. And thank you for coming to the gem5 tutorial this year at ISCA 2024. Broadly, our plan for the day, I'll introduce everybody in one moment here, but I am Matt Sinclair. I'm one of the members of the project management committee for gem5, along with Matt Premba here on my left, who is another member of the project management committee from AMD Research and Advanced Development. Jason Low-Power is stuck in some sort of interminable flight, hell. So he is going to be presenting remotely for his part. And then we also have Alan Cebu from NUS in Singapore and Vishnu Ramadas from Wisconsin, who are each going to be presenting different parts of the talk today. And ultimately, what we're trying to do, or we're going to do today, we'll do our introduction first before the coffee break. Then between that and lunch, we will start talking about broadly using gem5, the standard library, gem5 resources, and how you get LPs running with it. After lunch, we'll then talk about how you can extend gem5 and run different things that you might be interested in it, because of course, I'm assuming that's why the vast majority of you are here. And then after the last coffee break, we will finally talk about how the work we've been doing recently on getting machine learning workloads in PyTorch to run in gem5 and how we use gem5's GPU model for that. So that's the broad plan for the day. There is going to be some talking, but a lot of these sections are intended to be interactive. So we have a GitHub Classroom or code space setup that I'll talk about in a few minutes here. And basically all of the examples we're going to go through with you are intended to be interactive. So, the four of us in the room will be circulating around and coming and talking with everybody as appropriate in those sessions to help you if problems arise, and inevitably they will. We've tried hard to make them as user-friendly as possible, but of course, we can't anticipate every single thing. So if you have a problem, don't hesitate to raise your hand or reach out or ask. We are happy to help, and in the fact, that's why we're here. All right, so without further ado, the first section of the introduction, what we're going to talk about is what gem5 is, a bit of the background on it for those of you who might not be aware, and I'll add a couple slides of discussion about architectural simulation, how gem5 does architectural simulation, and then we'll start talking about getting started using gem5. Any broad questions or audio issues before we get too far into the weeds here? Okay, great. So, a bit of history first. As I like to tell students at Wisconsin, if we don't learn from the history, we're doomed to repeat it. So I think it's instructive to know a little bit about the background. Originally, gem5 was two different tools, and one of those two tools was the M5 simulator that was created in Steve Reinhardt's group at the University of Michigan, principally by Nate Vinkert, although along with several other people. And at the time, they called it a tool for simulating systems, which of course is a massive understatement, but nonetheless true all the same. And you can think of M5 two different ways, depending on how you'd like to view it. You can view it as a framework for event-driven simulation, where it takes events, objects, statistics, and configurations, and uses that to either pass information out or set up the system to model what you'd like it to model. Or you can think of it as a collection of predefined object models, things like CPUs, caches, buses, devices, and so on. Now, both of these views for M5 are true, but in this tutorial, we're going to focus on the second one, because in my opinion, that second one is probably what you really want to know, right? Like you probably want to know, how do I take what's already there and either use it straight away or tweak it a little bit to get the kind of information I want. And so while we're going to focus on number two, you might find number one useful nonetheless. Now, M5, sort of as it was designed, although there are some exceptions, was primarily focused on doing really high fidelity modeling of CPU cores. And while it had some modeling for the memory subsystem, there was a second tool at the time called multifacet gems, or just gems, from the University of Wisconsin, primarily by Mark Hill and David Wood and their students, that its claim to fame was that it had a very detailed memory subsystem that was highly configurable, and it'll allow you to model and study things like coherence protocols in multi-core systems. And so the way that worked is, as the the name might imply, everything was named after some sort of gem. They had an Opal processing model, which at the time was an out-of-order Spark CPU. That part did not advance to gem5, but was how they modeled the core at the time. And alternatively, that relied on a CIMIX, which you can think of as a single cycle functional only CPU. So it allowed them to get the correct answer, to make sure that their Opal processing model, when they used it, was getting the right answer as well, but was largely, fast forwarding, if you will, through the nitty gritty of the microarchitecture for the CPU so they could focus on the memory subsystem. And then they had different inputs that could be passed in to the memory subsystem, a random tester, which, as the name implies, allowed you to test, sort of random different things, as well as a variety of deterministic, contended, or trace file microbenchmarks. And these would be fed into the Ruby memory subsystem, where they had detailed models for the interconnection network, for the caches, and especially for the coherence protocol and the consistency model. And this allowed them to, of course, get critical mass, and is widely used and widely cited today. But each of them kind of, M5 and GEMS, kind of had the thing the other needed. So GEMS had this highly detailed, highly configurable memory subsystem. M5 had this highly detailed but less configurable memory subsystem that went with its highly configurable CPU model. So if you will, the M5 CPU model went really well with the GEMS memory subsystem. And so that's where gem5 came about. So it came about by combining the strengths of those two tools into a new platform. And what gem5 allows users to do is it allows them to have a single modular platform for computer system architecture research that encompasses not just the processor microarchitecture, but increasingly encompasses also the system level architecture. So it allows you to do co-design at a deep level in the modern day. And the two citations I have here are sort of the canonical citations for the tool. The original gem5 simulator paper that was in the mostly now defunct computer architecture newsletter, which the SIG Arch blog has kind of replaced today, and our archive paper in 2020 that we released, 2021, excuse me, talking about the modern versions of Gem. And largely, we're going to talk only about those modern versions today. So in 2020, Jason LaPower, myself, and a whole host of others that you're going to see on the next slide, kicked off what we like to call a regeneration of Gem5, or to enable a new era of computer architecture simulation. And in my opinion, this is really important because, as I'm sure you all know, our applications are getting increasingly diverse, increasingly complicated. We want to run systems that have many different types of processors, that have much more complex memory subsystems, and need to do co-design at a deeper level than they could before. And so this meant we needed to enhance the tool significantly, which is why you can, if you went and looked at the author list for that Gem520 paper, you can see that there are, no joke, exactly this many people. Of course, Gem5 is an open source project. We always welcome contributions from everybody, including those of you in this room. And so hopefully in the next version, you can add your name to this illustrious list. By the way, I will admit that last night when I was looking at this slide again, it took me like 30 seconds to find my name because the font is that small. So don't worry if you can't see it. Now, let's get a little bit more. So Gem5's goal is that we can take the entire computing stack from the application down through the runtime of the compiler and the kernel, through the ISA and the microarchitecture, and down to devices. And if you will, most simulators, their current domain is the ISA and the microarchitecture. So they're going to ignore things like operating system calls or compiler passes, and they're going to assume that's kind of passed into them. And that's somewhat short-sighted because the domain of computer systems research really encompasses that entire stack. And if you saw either electronically or in person, the Turing lecture from Hennessy and Patterson about 5 years ago now, they talked about as we're entering this second golden age of computer architecture, we need to have agile hardware development methods where we can iterate rapidly all the way up to tape out from C++ through all the different levels, including FPGAs and tape out and so on in between. And so this means that our tools need to adapt and evolve to meet that goal, right? Like if we're only simulating the architecture in the ISA, we're just not going to be able to help users do model and do the research that they want to do across the computing stack. Put another way, if we're only doing that part with the little arrow on the left, where we have the ISA and the mark architecture, then we're only doing that one little part. And so as part we're trying to make it so that anybody, including non-architects, which might even be some of you in this room, can download and use gem5 and not just use it to study the ISA and the mark architecture, but also use it for cross-stack research. So if you want to change the Linux kernel, or you want to change the runtime, which you're going to hear Matt and Vishnu talk about when we talk about the GPU work today, we support different versions of AMD's GPU runtime. Or you want to change the hardware, like say you want a different type of CPU from a different ISA. You can make all of those changes in concert in a single package. And you can even run the entire machine learning stack from, say, PyTorch, which we're going to talk about today. Maybe the full AR, VR stack, or other emerging applications as you might be interested. And just to be upfront, there's a lot of rough edges. This is always a living tool, and things change rapidly over time. So if it's not perfect today, hopefully don't take that as a discouraging sign. Take that as a sign of a place where we as a community might need help. And if you're willing to help us solve those problems and contribute it back to the community, that means everybody can benefit. So we're getting very close, and we, the four of us, and Jason remotely, as well as a lot of other people who are shown on that list a few slides ago, invest a lot of time and effort to make this tool easier to use, to make it more higher fidelity, make it more replicable, so on and so forth. There's a lot of ongoing efforts that we're not really going to talk about today to achieve those kind of goals, in addition to the more classic research that we're going to focus on how we can enable that. So with that said, right now our community has hundreds of contributors and thousands of users. At least we think it's thousands. It's kind of hard to track. We can see how many people download gem5, but we can't track how many people use it on a daily basis. Ultimately, though, our goal is to meet the needs of academic researchers, which I didn't ask in the beginning, but I'm guessing the majority of you fall into that category, as well as industry research and development. So AMD, ARM, Samsung, IBM, Google, and many others that I'm sure I'm forgetting, all use gem5 in some shape or form in their research labs in those companies. And increasingly, national labs, not just in the US, but also in other countries like Japan, are also using it to fund, or not to fund, to perform their early stage design development with gem5. And then lastly, of course, we want to make it so that new students, those who are coming in and haven't used gem5 before, can use this in the classroom. And so we have resources we've been developing, and I know Elva's not here at the moment, but she'll be here a little bit later. She is working with Jason and I and others on trying to develop a sort of canonical set of resources that we can release to teachers if you're here in your classroom. And we also have, in recent years, been working on making the community more inclusive and welcoming. So we've developed documents like a code of conduct, which you can see online. But ultimately, we're doing all of this, and we're trying to make it easier to use, more accessible, and so on, because we want to see the community grow, right? Like each of us, in some way, shape, or form, has used gem5 for a long time and believes in its potential to achieve our research goals. But we want to try and make it so that it's possible for you all to achieve your goals as well. Okay, so I'm going to talk a little bit more about simulation. And that comes back to that idea, that agile development model that Hennessy and Patterson were talking about in their Turing lecture. So in that lecture, they were talking about how we need to rapidly iterate from C++ all the way into async. If you think about that from a different perspective, and this comes from Lieven Eckhout's synthesis lecture on computer architecture performance evaluation modeling. He was comparing scientific research, if you will, the scientific method, where we have some sort of hypothesis. And so we design an experiment, we run that experiment and try to quantify the results. We interpret them. Of course, sometimes those results don't match what our expectations were. And thus we go back to the beginning and depending on the results, either come up with a new hypothesis or we design, some new experiments to get additional data. And eventually this process will terminate once we find the results, solve the problem that we believed we were going to do. Systems research follows a similar pattern, except in that third step where we were running experiments and quantifying, oftentimes we're trying to do this on future systems that don't necessarily exist today. And that's where tools like gem5 come in handy because they allow us to take models of relatively existing parts and add support to them to model whatever research we want to do while being confident that those results are somewhat high fidelity based in reality and thus realistic and useful. So while there's other changes as well here, for example, when we design the experiment, we need to pick some baseline system that we want to run on and the workloads we want to run on it. And when we analyze those results and find they don't necessarily match our intuition, maybe we need to pick a new design instead of picking a new hypothesis. Ultimately, the research we all in this room are doing is very similar and based on the scientific method itself. So oftentimes to achieve those goals, we need tools like gem5 simulation and modeling tools to determine if our ideas that we want to implement are any cool. Good. So we put another way, we need a tool that allows us to evaluate systems that don't necessarily exist and to determine what the performance would be, what the power or energy would be. Maybe even, someday we want to look at other factors like sustainability that don't exist yet. Or we maybe want to look at things that do exist like network traffic. Those are entirely other things that we might care about in these systems. Naturally, taping out processors, even if the Hennessy and Patterson talk said, discuss how we make it. It is very costly to actually go through that process and tape out that chip. One of my colleagues at Wisconsin, he recently went through a startup where they were taking research from his lab and making real processors out of it. And it took them, about 18 months to 24 months to come up with their first piece of silicon. And, depending on, I always ask students in my classes how long it take them for those who worked in before they came to grad school. I've never heard anything less than 12 months, but I've also heard all the way up to, 2.5 years to get to tape out these, to get your first piece of silicon. So the costs are very, very high to create that first chip. And we don't really want to wait 2.5 years to take our idea. Let's say you have some great idea called foo, and foo is going to solve all the world's problems. You don't want to wait 2.5 years to find out that it's a good or bad idea. We need to have some ability to understand if that's going to be good before we commit to this costly process of taping out silicon. And this is challenging because computer systems are complex, right? We have all those components that I mentioned a couple slides ago: caches, and memory, interconnects, and microarchitecture, and interaction with runtimes, and compilers, and applications, and many, many other things that I forgot to mention there. You really need to have a tool that can model the entire system and those complex and sometimes subtle interactions in order to be confident that your idea is useful, that the research you're doing is going to improve the state of the art. And really what that means is you usually want simulation to be parameterized to allow you to do design space exploration, especially early in the process before you build silicon. And you can also do sensitivity analysis. Maybe you want to study if I sweep the L2 cache size from, 1 megabyte to 256 megabytes, how does that impact the behavior of my application? Well, ideally, you don't want to start from scratch and have to implement that design over and over and over. It'd be great. You can sweep that with, say, a push of a button. And these are the kinds of things that in the gem5 tool, we are either enabling, have enabled, or are trying to make it possible to do this full system study across the compute stack without relying on external tools, and giving you the ability to measure things like performance and power while sweeping the design space early in the process. Of course, simulators are not the only option. You may be familiar, if you haven't, with something called analytical models. Analytical models sort of sit on the other end of the spectrum for simulation and modeling. And so the idea with analytical models is we're going to use mathematical equations like Amdahl's law to do kind of the back of the envelope calculations about how good an idea is going to be. And so, of course, as you all know, with Amdahl's law, we can specify how much parallelism there is in the application, how much we speed up the parallel part, and that tells us what the maximum speed up we can expect to obtain for this workload is. And likewise, if we want to study queuing between components, we can use queuing theory or queuing models that take parameters like lambda for how many elements we're going to be putting in the queue, and mu for how much we're going to service in a given time. Excuse me. And they will then predict how long our queuing is going to take and how that's going to impact the behavior of our system. Now, the pro to these approaches is they're really, really fast, right? The mathematical equation, you can plug it into your calculator or Google Sheets or Microsoft Excel, and you can get answers right away. The downside is you're not able to do this kind of complex modeling that we just talked about on the last slide, and you could sort of convince yourself of anything if you pass it a particular number, right? Like, well, what if I just make the parallel portion of the application bigger? Or what if I make the speed up of that portion larger? Well, eventually you can, say, oh, great, like I get a much bigger speed up than I otherwise could, but it doesn't have any basis necessarily in what the application can actually do, how much parallelism it has, or how much speed up you can get. So while analytical models are a great alternative and have significant use and value in the community, you always have to be careful with them because just like simulators, they have some limitations. Within simulators, there's a large number of different types. Some of them are functionally based, so they're just trying to get the right answer. I mentioned the Symix processor when I talked about gems, something like that. You can also have ones that are instrumentation based or based on traces where you feed in a sequence of instructions and have it replay it and model the behavior of that sequence. However, today we're going to focus on the last two, which is what gem5 supports, which is execution-driven and full system simulation. In the case of execution-driven, unlike those previous three ones, where either we had a trace of instructions we gathered ahead of time that was feeding in, or we're trying to just functionally simulate it or instrument it, execution-driven actually executes all of the instructions in the program that you tell the system to run. So it is taking, say, backprop from the Rodinia suite of benchmarks, and it's running backprop from the first line of the code to the last line of the code. And all of the instructions in the ISA that go with that program are incorporated and included in that. Second, full system here means that we are actually modeling the interaction with the Linux kernel or with the runtime and the compiler and so on. So we are incorporating all of that into our tool versus if you were to do something that does not use full system, what that means is you're kind of just setting a boundary at the ISA level, and whatever happens above it, if you need a malloc memory or you need to run a compiler pass to remove dead code, whatever it might be, we just assume that that's been done before we reach the beginning of this program. So I kind of went through some examples of this on the past few slides, but just to reiterate, functional simulation, there's usually no timing information. It's just about getting the program to run correctly. Gem5's atomic modes are one example of this, but of course there's others as well. Instrumentation, that's things like binary translation. It's not really flexible to a new ISA, but it works well, say, for PIN in the CPU world or NVBit for NVIDIA GPUs. Trace-based and execution-driven, I talked about this already, the pros and the cons there. One con I forgot to mention is that trace-based, you're really locked into whatever sequence of instructions you captured. And if your program, say, has multiple threads and you only got one interleaving of it, well, your trace can't really capture that kind of information. And if it depends on timing between those instructions, you're really not able to capture that. Whereas execution driven, because it's combining functional and timing simulation, it allows you to get those kind of subtle interactions that are dependent on timing. I think I've covered the full system stuff already too, so I think I'm gonna move on beyond this. All right, so some nomenclature. When we in gem5, when we talk about the host, what we mean about the host is the machine that you're actually using. So say your laptop that you're going to run the test on today, if you weren't using our code space environment, that would be the actual hardware. That's where you're natively executing whatever program you might have. So you have some application in blue in the top right here. It uses the operating system in orange and then runs on your host hardware in yellow. In comparison, a guest refers to when the code is kind of running on top of a, if you will, fake a piece of hardware. And usually what this means is we have the OS running as a guest OS in a virtual machine. So something like VMware would come into play here. And because we're running that OS on top of the hypervisor is emulating the hardware. So the host would still be that yellow box at the bottom. But now we have this green layer for the hypervisor that's interposed between the application, the operating system, and the underlying hardware. Now, just to move through a little bit further here, with simulation, the simulator runs on the host. And essentially what it's doing is it's exposing the hardware, and I'm using hardware here because the simulator is modeling the hardware, to that guest, which will run the simulated hardware. And here the OS is running on gem5. Running on gem5 is the guest OS, and gem5 is simulating the hardware. So that yellow box is essentially become gem5, and that blue box, which was the hypervisor before, has now become the gem5 or this whatever other simulator you might be using. And so the simulator's code is going to run natively on the underlying host, which will execute or emulate that guest code. And the guest code will now become or a benchmark or a workload, whatever it is you might run. Because we have now replaced the real hardware with the simulator, it runs on gem5, not on the host. Any questions so far? Yeah, what's up?
Gem5, is that hypervisor?
So gem5 is not a hypervisor, but it's sort of taking the place of the hardware and the hypervisor. So when you run your application, you can think of it, it's not exactly like this, so maybe it's a bad analogy, but it's the one that works for me. You can think of it as all of the calls that the operating system and the application were sending to the hypervisor to emulate on the real hardware, we are intercepting them. And it's not that we're truly intercepting them, it's really that gem5 is running and modeling each of them. But the reason I use the word intercepting is it's like, say, when you did malloc, that malloc call, instead of going to the operating system down to the hardware and getting some addresses and sending it back to your program, instead it goes to gem5, and gem5 will simulate the process of identifying a sufficiently open page in your system and send that back to your program. So gem5 is taking the responsibilities of the hypervisor and the responsibilities of the hardware and mimicking them in whatever system you have gem5 trying to run. And the reason why I'm trying to distinguish this from the underlying host hardware is you can have gem5 be running, say, a GPU program or an accelerator program, but the underlying hardware could just be an Intel or AMD or ARM, whatever it is, CPU. So because gem5 is written in Python and C++, you can simulate different kinds of processors, even if the underlying native or host machine does not have those specific devices. So that's why I'm saying it's intercepting it, or it's mimicking the behavior of those things. Make sense? Good question. Anybody else? Okay. All right. So we've already talked about the first two of these, but a couple more things. The simulator's performance, remember, the simulator is running on that real hardware, but it's mimicking whatever it is, whatever system, as we just talked about, that we want to simulate. And so that means the simulator's performance is the time it takes from when you hit go until the simulation finishes. If you will, that's the wall clock. So it took n seconds or n minutes or n hours, however long it took from go until the simulator returned. That's the simulator's performance. However, because the simulator is running on this underlying system and modeling often at deep high fidelity the behavior of many different components, the simulated performance is the time that the simulator predicts your application would take to run on whatever piece of hardware you're asking the simulator to model. So again, just to use the same example, if you wanted to pretend that you're running on an AMD GPU in Gem5, even if there's not a real AMD GPU in your system, because you're running Gem5 on, say, an x86 CPU, within the simulator, we will predict how long that application takes to run in the simulator, i.e., like how many cycles do we think it would take to run on that simulated GPU. So this is, if you will, the time for the guess code to run on the simulator. And the reason why it's really important to distinguish these two is Gem5, because it gives you lots of details. The wall clock time can often be slow, but it will tell you in the statistics how long it predicts that application takes to run in whatever it is you're modeling. And that will usually be much faster. So just keep in mind that there are two different pieces of information here. Question? No? Okay. Okay. So naturally, in what I just said, there's some trade-offs to that, right? So there's development time. So that's how long does it take to modify or update Gem5 to model or simulate what I need. There's evaluation time, which is literally how long in terms of wall clock does it take for me to run Gem5 or any simulator to do the experiments that I want to do. There's accuracy. How faithful is the simulator relative to the real hardware that maybe I'm trying to model. There's coverage. So can I use the simulator to model many different types of components? And each of those 5 different simulation options that I mentioned a few slides ago has different pros and cons when it comes to these. Full system simulation or full execution-driven simulation often takes a while to develop, and the experiments, because it's running very detailed experiments, is very slow. But its accuracy is usually very good, and its coverage is usually very good. And this is contrasted, say, to functional simulation, which has very low development time because you're not trying to model every last detail. You're just trying to get the right answer, which means you can also evaluate things relatively quickly. But your accuracy relative to real hardware and your coverage relative to real hardware are going to be very poor because you weren't trying to model those things. And every one of those other approaches in between has its own trade-offs when it comes to these vectors. So ultimately, we are trying to make these tools easy to use, but I want to point out that there's some pros and cons. And what that really means, if we go back to Lieven's picture, is you should think about what level we want to simulate. So you should ask yourself, what fidelity is required to do these different things? So if you want to say do a register file design, you might want to make a relatively low level design, but sometimes the answer is a mix. Maybe I want that low level register file design, but I also want to study how some compiler optimization behaves. Well, Gem5 is very well suited. We have multiple different models at different levels of fidelity, and you can essentially in Python swap them in and out as drop-in replacements without needing to go and recompile your code, which is extremely valuable. However, this is where how the fidelity comes in. Those models are not guaranteed to be like bit by bit accurate with the real hardware you might be trying to model. And that's why we refer to them as cycle level as opposed to cycle accurate, because we're not guaranteeing that everything behaves exactly the same. But we're getting the trends pretty close, and that's why we call it cycle level. There's also RTL simulation, where you say implement something in Verilog or VHDL. And here the model is your hardware design, and you've specified every single wire, every single register, every single ALU. It's pretty close to the actual ASIC. And this is going to be cycle accurate because it's exactly whatever hardware that you intended it to model. But of course, the downside here is that it's not as configurable. You need the entire design to be implemented in HDL or Verilog. It's more difficult to combine functional and timing, but it's super accurate relative to that real hardware. In comparison, cycle level, because we're just trying to get those trends right, it models the system cycle by cycle, usually in this event-driven way I've referred to a couple times. And it's not the same as an ASIC, but you get similar timing. And for that downside, the trade-off is that it's easily parameterizable. You don't need full hardware design. And it's usually faster than cycle accurate because we're not modeling each and every one of those details. We can round off a few of the corners and trade them off to improve simulation time. Okay. I have about 5 more slides, it looks like. I know we're running a little bit late because of the AV issues, so I do apologize for that. We'll keep going here. So in terms of gem5's architecture, there's 3 key points that I want to make here. First of all, gem5's models are written in C++, and it has hundreds of such models. These models can be for things like caches, which have a parameter like what size or associativity or line size do I want the cache to have. It has a variety of cores where your parameters might be, is it in order or out of order? If it's out of order, how wide is it? What's the LSQ size? How many stages of the pipeline are there for in order or out of order? For main memory, we have parameters specifying, row and column access latency or size and so on. These are all written in C++. And you can think of them as being components of whatever it is you're trying to model. But what gem5 does with those components is it will allow you in Python to specify some system you want to implement. So here, the picture we've drawn is you have, say, 2 Intel Core i7 processors with an L1, I, and D cache that are split, and then a combined L2 1 megabyte unified cache. And below that, maybe your memory subsystem has DDR4. In gem5, we express all of this in Python, and we will specify specific components, say in this case, the CPU that's Intel i7, the caches with their appropriate sizes and structure as shown here, and then DDR for the main memory. And we pass that information in, for example, cache size, as parameters to specific models. So we set those parameter values in Python, and what the Python will do is it will control the C++ models that we have and tell them what we want to model in a given run. So the components are models with a particular set of parameters. And we control that in Python. And it's not just that we control the configuration of the system we want in Python. We also tell it in Python where we want to start. If we want to reset the stats or dump the stats, when we want to stop the simulation, and so on. So the key idea here is that it decouples the actual models that are written in C from a given simulation, what you are trying to configure and model. So you can develop experiments with these key parameters and then easily configure them. Say, again, we talked before, what if I want to sweep L2 size? Well, all I have to do is change that value in Python, and then it's going to tell the underlying C++ models to use the appropriate size for the L2 cache and run the same or similar set of experiments. So it's quite powerful. The way that gem5 does this, though, is with something that we call sim objects. And what sim objects do is the model is C++ code, which will be in the source folder of gem5. The parameters are Python code, which is also in the source folder, but they're explicitly specified in the sim object declaration file. And then the instance or configuration is a particular choice for the parameters. So in the standard library, this would be your extensions or a Python run script. And in the next session after the break, we'll talk more about the standard library. What this means in terms of modeling versus parameters, as I alluded to, we have this generic model in timing written in C++. We expose those parameters to the Python. So say we can specify things like cache size or associativity or latency. And by setting them in Python, we will then construct the underlying system. For example, maybe something that looks like this, which is a relatively complicated out of order processor with split L1 I and D cache with a load store unit, and then say a 512 KB 8-way set associated L2 cache connecting them on the back end. So again, the key idea here is by decoupling these generic C++ models and associativity, size, latency, whatever that they might model from the configuration that we do in Python, it allows you to rapidly change what it is you're modeling. Again, for example, changing the L2 cache size without needing to go and change those underlying models. And you can also extend models. So let's say you want to design a new class. Well, what you would do is you would want to inherit from the objects that exist in C++ already. So for example, with our out of order or O3 CPU, we inherit from the base CPU class, and then we can add things that we want to specialize in that model, which will inherit from the object in Python. So for example, in an out of order CPU, we want to set the issue width, and we can inherit from the class in Python that says we want that issue width to be size 10 or whatever size your part would like to be. Lastly, you heard me mention a couple times that gem5 is discrete event simulator. And what we mean by that is every time something is going to happen in the simulator, say we want to model some sort of instruction being performed or a memory access, whatever it might be, we will place an event on an event queue. And the way the event queue works is you will dequeue whatever event is at the head and perform that operation. So we execute that operation. And that operation might generate more events that get placed on the tail of that queue. Or maybe they just happen later from some other instruction in the program. And this process will repeat over and over and over. We dequeue the event at the head. Maybe it generates something. You might notice, though, that each of these events have a time that we want them to happen. And this is how we specify things like latency. So we're saying in n cycles or n cycles from now, I want this event to happen. And so because this event we wanted to happen at timestamp 51, we placed it earlier in the queue as opposed to the head because that's when we want it to happen. So this event queue is essentially ordered by what needs to happen next. So all the sim objects in our system can enqueue events to the event queue, and they're dequeued in the order that time wants them to progress. So what that means is, and if time is on the x-axis here, at the beginning of time, we fetch the first instruction. It might send a request, say, to the iCache, because we need to figure out what that instruction is. That iCache has some tag latency to do that access. And so that means sometime later, we'll actually do the access at the L1. If it misses in the L1, well, then we need to send it to the L2, or if there's no L2, to the DRAM. And again, there's some latency to do that access. And so when we enqueue that event, we would want it to be enqueued with the latency difference between the current time and the time we believe it takes to access the DRAM before we actually do the read at the DRAM. So there we do the read, we access the DRAM has its read latency. So again, we enqueue with some time associated with it. We finally then get the data from the DRAM at that point, and now we respond back to the core. The cache receives the data, and then one cycle later, the processor gets the instruction and can decode it and execute it. So the key here is because each of these things are being treated as an event, they will each be placed on that event queue with the appropriate latency of that action, and that allows us to model the behavior of this real system, because just like a real system has cost to doing each of these, so too does gem5. And then, of course, this process repeats, and we do it for the next instruction. Okay, so what that means is time on the x-axis on the previous slide needs some sort of unit to go with it, right? Because we said there's some latency associated with each of these events. In gem5, we call that unit a tick. And we need to convert a simulation tick to some user understandable component, like seconds. And this is what gem5 calls the global simulation rate. And the standard approach is that 1 picosecond is 1 tick, which means there are 10 to the 12th ticks per second. Okay, so to summarize, in gem5, we abstract a number of things to allow the user flexibility to configure what they want. So you can choose different CPU ISAs, different CPU models, and different ways to abstract memory requests. And to do this, between the different components, we have ports that allow you to send requests and receive responses. Ports are unidirectional, so you can have a request port or a response port, and anything, with one exception, which we'll come to in a minute here, with a request port can be connected to any response port. So if I want to model, a system that let me go back quick, sorry. If I want to model a system with a CPU followed by the split L1 caches with crossbar to the L2 cache and then to the memory controller, what I would need to do is I would need to have a request and response port connecting each of those components. But the reason why I said any is it does require that you've implemented the interface to do that connection. So if you have some new CPU model or a new ISA that you want, you can integrate it in as long as we have that definition here. Okay, so hopefully what that's done is given you a bit of background on what gem5 is, how it works, and in the next sessions, if you will, the next sets of slides, we're going to start going into the details of how you actually do that. Since I think there's 5 minutes before the coffee break though, are there any questions I can clarify about any of this? Because I think it's probably going to be better if we start the next part after the coffee break. No questions? Okay. So Jason, just to coordinate with you for a moment, are you okay then if your part starts after the coffee break?
Yeah, that sounds good.
Okay. Well, then why don't we take a pause here and go use the restroom, get a coffee, whatever it might be, and we'll be back in 20 minutes, right? 20 minutes.